Bismillahirrahmanirrahim. This is our lecture number 4 of oxidation reduction course. And today's topic is Swern oxidation. We will discuss about the oxidation process which was designed by Swern. We will discuss its oxidation, oxidizing agent which are used in Swern oxidation and mechanism of the reactions with some examples and then synthetic utility of this reaction. फर्स्ट ऑफ ऑल डियर स्टूडेंट्स स्वर्ण ऑक्सीडेशन ये एक ऐसा प्रोसेस है जिसमें हम सेकेंडरी अल्कोहल स्पेशली हम इसको ऑक्सीडाइज कर सकते हैं in the presence of DMSO. DMSO is now dimethyl sulfoxide. It is an oxidizing agent. Along with it, you will use oxalyl chloride. The presence of this oxalyl chloride activates this DMSO and it will act as a very good oxidizing agent for this secondary alcohol and it will give you this ketone. You will see that this reaction is very mild and these are mild condition. If you have primary alcohol, you will obtain aldehyde. No further oxidation will take place. So this is the synthetic utility of the Swern oxidation, that you can synthesize aldehyde from primary alcohol. In workup, you use this triethylamine. Now, the mechanism of Swern oxidation is composed of different steps. The first step includes the reaction of dimethyl sulfoxide, yani DMSO, with oxalyl chloride. And this is the structure of oxalyl chloride. Upon reaction, this will attack over here, and this is open, and then it comes back, and this leaves the surface. A sort of nucleophilic substitution. You will see that this type of intermediate is formed, which is decomposed to give you carbon monoxide and carbon dioxide and give you this type of sulfonium ion. This is dimethyl chlorodimethyl sulfonium ion, which is very active species and is helpful in the oxidation of alcohol. In second step, this active species sulfonium ion, chlorodimethyl sulfonium, will react with alcohol and it will give you this type of intermediate, and which is further decomposed in the third step and in the presence of any base. In this case, we have used triethylamine, and this triethylamine will obstruct this proton and this will comes here, and you will get electron pair from here, and you will get this type of species, and then this electron pair will obstruct this proton internally and this electron density come here and you will obtain aldehyde from this primary alcohol. And if you start with a secondary alcohol, then you will get secondary alcohol, you will get ketone. So this is very simple process of Swern oxidation. There are some byproducts in the Swern oxidation, that is dimethyl sulfide, carbon monoxide, and carbon dioxide. As you know that carbon monoxide is very toxic gas, and there is possibility that this toxic gas may get we inhale, and it is attached to hemoglobin, carboxyhemoglobin is formed. So that is why this process should be done with very care. And the one thing that is very important, or advantage of this Swern oxidation, is the formation of these volatile byproducts. These can be easily removed from the media, and you can carry out very easy workup, and you will get the in very good yield your corresponding aldehyde or ketone. This data is from some literature, and here instead of oxalyl chloride, this type of chloropropene has been used, and it has the same function as oxalyl chloride in the presence of DMSO, which is an oxidizing agent. It will oxidize this secondary alcohol into ketone in the presence of this base. Similarly, this aldehyde this alcohol, sorry, this is secondary alcohol, and it is converted into ketone in the presence of this oxalyl chloride, and this type of derivatives of dimethyl sulfoxide. Instead of dimethyl sulfoxide, they have used this bulky alkyl group containing methyl sulfide. Synthetically, swan oxidation is very important. It is a mild condition. One thing, you will get aldehydes, they will not react further, and it is very good method for the preparation of aldehyde. And number two is that it avoids the use of toxic metals like chromium, and it is a mild condition. So this is the synthetic importance of swan oxidation. So this is end.